Nobody knows what I ate in the morning. I ate breakfast rice. I don't know. We're looking at kinetic molecular theory of matter. Get ready. This one's a doozy. It's one of the longer derivations we'll do. So let's get started. Before we even begin this derivation, we need to set up 4 ideas that we are going to assume to be true. Okay, these are 4 initial assumptions that as long as these assumptions hold true, then we can go ahead and use the KMT, the kinetic molecular theory of gas. Our first assumption here is that we have a large number, n, of mass, m, acting in random speeds and directions. So I guess we could have just said there, random velocities. That's the first thing that needs to hold true. We say a large number, we don't mean like 100. We mean like hundreds of thousands, millions. We're talking very large numbers. We're talking numbers so large that when we use that term large numbers, we're talking about statistics size large numbers. So that's the size of numbers we're talking about, okay? So this large number, n, of mass m, acting in random speed and directions, it's a big quantity here. The second thing that we need to think of is that every molecule that we are dealing with here are far apart. What we mean by this is that our molecules are not going to just always be running into one another. They're not so densely packed that they've all of a sudden like act as a solid or something weird. The molecules are far apart. They're allowed to move around in their random speed and direction and act as a gas. The third thing that we're going to say is we are going to assume that classical mechanics works. Specifically, we need momentum. And we need to conserve this momentum. You might say to yourself, Mr. Botzer, if we're at the atomic scale, classical mechanics gets all trippy and we start needing to use more advanced mechanics. Yeah, for right now, no. We're just going to assume classical mechanics works, and we're going to conserve a lot of momentum here. That's where we're at for this idea of the kinetic molecular theory of gas, and that will take us through what we need. Our last point that we're going to have is that all collisions are perfectly elastic. We are not going to lose any energy internally. When a gas molecule would hit a gas molecule, even though they really won't, they're far apart, no energy is lost. If a gas molecule hits the side wall of a container that it's in, no energy is lost. No energy is lost in this system. It's perfectly isolated and contained, and all the collisions, therefore, are perfectly elastic. These are the 4 initial assumptions that we need just to begin this derivation. So with that in mind, let's begin. We'll first think of a vessel. Imagine that we have a container. It's a box. And we're going to say that this box, every side of it has some dimension, L, some length, some width, some height, that exists. And we are going to say that within this box, there is a particle. Technically, there's a large number of particles, but for right now, let's just say that there's one, so we can keep track of it. This particle is at the moment moving to the right. If we go back to collisions, and what we learned in classical mechanics in regards to collisions and momentum, when we have a change of momentum, a delta p, and remember that momentum is a vector because there's a velocity, that change in momentum is equal to a mass times a change in velocity. This change in velocity is very important here because what we're saying is it's a mass multiplied by a final minus initial direction and amount. When our object here is moving to the right and it hits the sidewall, it begins moving to the left on this perfectly elastic collision. This means that not only did this particle have to hit the wall and stop and lose its entire momentum, but it then regained it acting in the other direction. So the actual momentum change here that we get out of this particle is actually equal to twice the mass and velocity it had initially, because it had to lose all that velocity and then it gained it all back. So it went through twice the velocity change for that mass. The change in momentum then is 2mv. Let's also just assume for right now that this particle is only acting in the x direction. It's acting one-dimensionally. We're going to have to expand this out into 3 dimensions later because random speeds at random directions. But for right now, let's not go insane, and let's just say it's in the x direction. Now, for this particle to move across the box and then back to make an entire loop here, we can easily find that out. We can say that the time it takes for this to occur is simply the entire distance, 2 times the length of the box, divided by the velocity of the particle, which we've designated as Vx. So right now we've just stated that, look, this particle is going through a change in momentum when it hits the sidewall and bounces back, and it takes some amount of time to go from one edge of the box back to where it started. Now, why does this even matter? Well, if we want to go back even further into classical mechanics, we can use my all-time favorite equation. F equals ma. If you've dove deep into the calculus portion of F equals ma, you may recall that acceleration can also be written as DVDT. It's a change in velocity in some amount of time. But we don't need to write it in the differential form here. We can simply write this as m times some change in velocity in an amount of time. Now, why is this so important? Well, this is an m times delta v. M times delta v is the change in momentum, which we just said was 2 times the mass times the velocity in the x direction. We also know the time is 2L over Vx. So we can say that the force acting on impact here is equal to 2m Vx divided by 2L over Vx. Which, if you want to pare this down a little bit, this will simply give us m Vx squared over L. Our 2's have canceled out. The Vx comes up. Questions, comments, concerns on what kind of hocus pocus we've just gone through to this point in time? Aiden, talk to me.
How did you get the change in velocity for like the...
Right there?
Yeah, how did you get the two mass velocity?
So, m delta v, this numerator here, that is a change in momentum.
Oh, okay.
Since we said change in momentum was 2m Vx,
Yeah. Okay.
I plugged it back down.
Okay, I gotcha.
Other questions, queries, making sure we're on the same page here of all this hocus pocus going on. Okay. Let me see what I want to say next so I don't mess up this video. Geo.
I guess what's the goal? Like, what are we trying to reach with PM delta V? What are we trying? What's the angle that we're trying to reach? What are we trying to work out?
That's a wonderful question.
Okay.
Remember how PV equal to energy?
Yes.
That's assuming that if you have some gas at a pressure and some volume, it has some energy associated with it, right? What is that energy? Can I actually create something that tells me anything about that energy? Or even better, if I've got all these molecules moving at random speeds in random directions, can I find an average velocity of them? Because if I can find an average velocity, then isn't that velocity related to a kinetic energy? And isn't temperature nothing more than the average kinetic energy of particles? And if we know that nRT is equal to PV, now we've just linked the whole thing. So, I'm going to be honest, it's not clear that this would take us there, but it will. And we'll start seeing as soon as I flip my page and we start getting into bigger stuff that it all comes together. It always comes back to energy. Yeah, it always comes back to energy. Okay, so what we see now is that our force is going to equal the mass, and we're assuming that all the gas is the same mass here. And then we're going to have some number of particles in there. And then these particles are all moving at some average velocity squared in that x direction. So now we're taking like this idea in the top right here, and we're applying it into our equation. And this is all divided by a length. When we combine this here, we see we have the following. We see that force is equal to the mass times the number of particles times the average velocity in any random direction squared divided by not only L, but 3. Because we took this 3 here, divided it, because we had to find what Vx was. So this right here is the force acting on our vessel from every single particle moving around and bouncing off of its container in random directions at random speeds, which we've averaged out into this average velocity. Having this as a v square is nice and helpful. One, because it actually moves and propagates through, because it gets rid of the square root in our Pythagorean theorem equation. But it also is going to pop up because now, since it's squared, we don't care about direction. Positive and negatives mean nothing to us anymore because when we square them, they'll all become positives. Now, from here, we have this force, and notice that there is a length in our denominator. Well, what we can do from here is let's start thinking about pressure. We know pressure is a force per unit area. So what we can state here is that this force, which we could write as 1/3, that's the 1/3 right here, times mn average velocity squared, this can be divided by AL. The L came from the original force equation, and the area came from the derivation of pressure. This, if we rewrite it, can give us 1/3 mn average velocity squared over a volume. And yes, I know that this looks a little weird that I've got the 1/3 up in the numerator, but there's a reason why I'm doing that. The reason being is I'm not going to keep this volume in that denominator very long. What I'm going to do instead is I'm going to take this volume and I'm going to combine it with this pressure. I can now say that PV equals 1/3 mn V average squared. That is huge because we already knew that PV equals nRT or nk delta T if we had the number of particles or molecules in there, which we currently do. So by starting to work into this, we're starting to see how we can start getting back into NKTs or nRTs and how we can start working this into ideas of energies. So what are we going to do from here? What we're going to do here is we're going to take this 1/3 and we're going to do something kind of weird to it. 1/3 is equivalent to 2/3 times 1/2. Because if you do that, you're going to get 2/6, which is 1/3. So I'm going to replace this 1/3 here with 2/3 times 1/2. Seems really weird and strange, but in doing so, something pretty awesome is going to occur here. We're going to get PV equals 2/3 n times the quantity of everything left over. 1/2 m v squared. And 1/2 mv squared is something that we should be very, very familiar with. 1/2 mv squared is kinetic energy. So because of this, we see here that we have some kinetic energy existing, which is a really wild thing to just kind of pop up in this pressure and volume equation. But it is something that we're going to need there. So what we can do now with this is, since we've recognized this 1/2 mv squared is kinetic energy, we can also branch and see the following here. We can note that this 2/3 times 1/2 mv squared, this actually has to equal kT, Boltzmann constant times the temperature. Because recall that PV equals either nRT or nKT. We already have the n here, so what we can say is that 2/3 times 1/2 m average velocity squared, that equals Boltzmann's constant, 1.38 times 10 to the 23rd, multiplied by some temperature. So what we can do now is we can say that kinetic energy here, the 1/2 mv squared, kinetic energy, we can just move this 2/3, we can multiply it over to the other sides to get 3/2 kT. So what we see now is that the kinetic energy of the molecules in this ideal gas as they're zipping around is equal to 3/2 kT, which, just recall, that is 1/2 mv squared, in case you forgot. Now this velocity squared that we had, we're going to end up solving for it to find out what that average velocity on the inside is. When we do this, what we're going to see quickly is that these 2's are going to wipe out. And what we're going to find is that this average velocity squared is going to equal kT over m times 3. When we take the square root of each side, we finally find this average velocity. Now this average velocity isn't just an average velocity. It is technically what is known as an RMS, a root mean squared velocity. What we mean by a root mean squared is actually going backwards, square mean root. When we found those velocities up here, up top, we first took the square of them so that we got rid of all the negatives. We then took the mean of them, so we weren't just looking at one, but the average of many. And then we found generalized directions by technically taking square roots at the very end here. This last square root allowed us to get us back into just velocity terms instead of a velocity squared. So this is a RMS speed or a RMS velocity. It is a root mean squared. And it's a nice way of getting values that are positive for your velocity terms so that you have speeds essentially for everything. So this is a big feature down here, this RMS velocity. That is something to keep in mind moving forward. The other big feature looking forward into the future here is that this kinetic energy was at one point equal to 3/2 kT. Remember, we only got rid of the 1/2 or the 2's here because when we did the math, they canceled each other out. But do recall that this did read at one point in time 3/2 and 1/2 here. This is very, very important. We're going to see why this is important later on because this 3/2 kT closely resembles what we're going to be using for the internal energy stored inside a ideal gas in all of the molecules there. So that 3/2 kT is going to come back in a very similar format with some additions a little bit later on. But for now, this kinetic molecular theory of gases for this matter, originally derived by the James Clerk Maxwell, is indeed finished. Thanks for making it all the way through with us. Until next time, adios, and take it easy.